current electricity, bringing it down to our own level and standard, because this can go to as far as in advanced nature, but bringing it down to UTME and WAEC examination, it simply means the study of the movement of electrons in a body, in a particular body. And there are peculiar parameters I would like us to discuss here. The first is the current, which you hear every day, but many of us, we don't even know what current is. And some of us think that yes, it's only current that brings about electricity. We'll soon find out. I would like us to discuss current, potential difference, and the law that is holding them together. First, we'll talk about current. Talking about current, this simply means the quantity of charge per unit time. That means if I have this board as my frame that I'm observing, the quantity of charge on this particular board within a given time interval is what we call current. So mathematically we define current as the quantity of charge per unit time, which simply means that I, conventional representation of current, is equal to quantity of charge Q all over time. Then the second one is the potential difference. Potential difference, which in another way we call the voltage. PD, potential difference. This is the work done in taking a unit positive charge from one point to another within the field. For example, if I have this to be a field and I have a charge here, and this is the field, if I'm able to take this charge from this point to somewhere here within the field of the charge, we say that I have undergone what we call potential difference, which is the work done in taking this charge from a point in each field to another point in the field. But if it's outside the field, we no longer talk about potential difference, but we talk about electric potential. So now, the potential difference, which is mathematically defined as PD or V, equal to work done per unit positive charge. Talking about current and potential difference, these two things together make us have what we call a sustaining electricity without hazard. When the current is there, it flows through the conductor and electricity flows, while the potential difference moves across the conductor, also for the generation and stability of electricity. Now, there is a law that governs them together, and the law was proposed by a man called Ohms. Ohms states that whenever you have a material that has a metallic character, or you call it a metallic conductor, that the current passing through that particular material is directly proportional to the potential difference across the material. That means if I have this to be a metallic conductor, for example, I have current passing through this material and I have potential difference across this. We say that the current passing through is directly proportional to the potential difference. Mathematically, we'll say that V, which is the potential difference, is directly proportional to I. And as I told you in other topics before now, that potential difference being directly proportional to I, proportionality sign is a dummy sign. And we have to get an equivalent or equal. And for me to put that, there must be a constant to take care of the consequences. So we'll bring in a constant which is known as resistance. So we'll say that V is equal to IR, where R is the constant of proportionality known as resistance, which is the parameter that opposes current. Resistance, which we just introduced as a constant, are produced by resistors. And I want to introduce and discuss the arrangement of resistors. There are two basic ways there you can arrange resistors. The first one, we have the series arrangement. The second one, we have the parallel arrangement. In series arrangement, there, note this, that in every series arrangement of any electrical component, the first thing you have to know is that the current passing through all will be the same, but the potential difference across them are not the same. So we said, since the current passing through them for series, current is the same, but potential difference PD varies. While this is for series, while in parallel arrangement, the current passing is not the same. While the PD across is the same. If you have this in mind, that in series, current is the same and PD vary, while in parallel, current is not the same, while PD is the same. Where will you see this kind of question majorly? JAMB students, listen. You always see this kind of question that says, which of the following is true? And they give you I call that question the terror of Nigerian students. But look at this, it will come. Which of the following is true? It will tell you in series arrangement, current is the same, I. In series arrangement, PD vary, I, and something like that. If you know it, you know it. If you don't know it, you don't know it. So now let's take the calculation from this particular area. In series arrangement, we have a formula for the arrangement of resistors for us to find the total resistance. For example, when we say series, we have something this way. These three now, they are in series. Why? Because the same current will pass through all of them. And since the same current will pass through all of them, if I call this R1, R2, and R3, in series arrangement, the resistance or the total resistance, or you call it the resultant resistance or the net resistance, is equal to just the summation, which is R1 plus R2 plus R3. But for parallel, it's not the same. For parallel, if I have my parallel arrangement in this form, where we'll have R1, R2, R3, such that the PD across them is the same, but the current passing through them vary, we can say that in parallel, 1 over the R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So in arrangement of resistors, take note of this particular thing, because in any given exam, this will answer at least minimum of 5 questions for you, as simple as it is. Find out when it's in series and know that it's just summation, and when it's in parallel, you know that it's the inverse of the summation. Then after that, remember to find the inverse of this, which is your R total, and that will be your answer. But no, this is only for resistors, because in capacitors that we are going to discuss now, the inverse remains the case. Arrangement of capacitors. The one we just finished is arrangement of resistors, but this one now we are discussing arrangement of capacitors. In arrangement of capacitors, there are also 2 basic ways to do that. The first is also the series arrangement. But this time, the series arrangement, we have 1 over C total equal to 1 over C1 plus 1 over C2 plus 1 over C3. While the parallel arrangement, we have the summation as C total equal to C1 plus C2 plus C3. In resistors, you will bear me witness that for series, this is the way it's looking like, the summation. But this time it's changing in capacitors. Don't be confused about them. For capacitors, the series is the inverse, while the summation is for parallel. While in resistors, the series is the summation, while the parallel has the inverse. Now from there, I will bring it down to arrangement of cells. Sometimes you use your little radio and you put your battery the way you put it, and you don't know what is happening there. Why is it that when you change the edge of the battery, the radio will not work? Let us discuss it now. There are 2 basic ways you can arrange cells. The first one is the series arrangement. In series arrangement, where we'll have the current passing the same, but the potential difference, they are not the same. So if the current is the same, That means in arrangement of cells, we say that the E total is equal to E1 plus E2 plus E3. This is for series arrangement. But for parallel arrangement, cell is different from resistors and capacitors. There is something going on there. For parallel arrangement, instead of maybe being the inverse, we have something like this. That when you set batteries in parallel, this way, let's assume you have 3 batteries like this, and all of them are facing the same point. What do we have? If this battery is 1.5, 1.5, 1.5, had it been a series arrangement, what we'll have is 1.5 plus 1.5, which is about 4.5. But now that it's parallel, someone will expect us to do something here, maybe 1 over 1.5 plus 1 over 1.5. No. In parallel arrangement of cells, the whole cell is serving as one cell. That means this 1.5 into 3 places is serving as one cell, which is 1.5. So we said in parallel arrangement of cell, the E total is equal to E1, is equal to E2, and is equal to E3. They are the same. Example, as we have here 1.5, 1.5, 1.5. If you ask us to calculate the total cell we have here, what we have is E total equal to 1.5. And that is the answer. Don't go checking the inverse. Now, from current electricity, we've taken the definition and description, and I told you what current is all about. The quantity of charge with respect to time. From there, we'll move down to Ohm's law, which states that V is directly proportional to I, and making resistance the constant of proportionality. And we show you the arrangement of resistance. Remember, in series is the summation, and when they are in parallel is the inverse of the summation. From there we'll come down to capacitors, which is an electric component that has the ability to store energy. And we've shown you the arrangement. For series is the inverse of the summation, and for parallel is the summation of all the capacitors. Now down to cell, and we have this, that E total is equal to E1 plus E2 plus E3. E total for parallel is equal to E1 and is equal to E2 and is equal to E3. It's the same all through. And we'll say that, example here I've given you that E total is equal to 1.5, while if it's in series, what we'll have is what? 4.5. That will bring us down to electromotive force, EMF. My dear, I know you may be wondering what is EMF. This simply means electromotive force. An electromotive force simply means, in definition we can say that it is the total work done in taking a unit positive charge round a complete circuit. You can see my circuit. Once a positive charge is produced, or a positive charge moving across, we say taking it round this complete circuit. The work done in doing that is called electromotive force. The force that will take this round a complete circuit. But mathematically, to make it reasonable to us, we can say that electromotive force is the summation of all potential drops in a given circuit. Now if you look at my circuit, join me here, follow up. If you look at my circuit, we'll say here you have R. We have one potential drop there, small letter V. And here we have the capital R, which is the load. And we have another potential drop, capital letter V. There is no other drop here. So we can say that electromotive force, E, is equal to summation of all the drops, which is small letter V plus capital letter V. But you can remember Ohm's law. That Ohm's law says that V is equal to IR. And we'll say that when they are in series, that the same current is passing through them. And if you look here, you see that they are in series, because the same current coming out from here will pass through this small internal resistance and move on. It will not jump out of the wire until it will pass through this place. So they are not in parallel. Some of us will, because this one is here and this one is here, they say they are in parallel. No. Don't look at the structure, just look at the passage of current, where it's going. So they are in series. And since they are in series, the current in them is the same. So we'll say that E is equal to, relating this now to Ohm's law, we have I small letter r, and the capital one we have the same I capital letter R, which I can factorize out on my I so that we have E equal to I bracket R plus R. This is my resistance now, the summation of resistance, which is the internal resistance plus the resistance of the load. This is the current and this is the EMF. So this now is the EMF of this particular circuit, which is the total current times the total resistance. I can find my current from here by making I the subject of the formula, so that we have E all over R plus R. And this is the equation of current when an internal resistance occurs. Someone may be asking, or asks you now, what is internal resistance? Internal resistance is the resistance of a generator or a cell whenever it is at work. If a cell is not at work, there is no existence of internal resistance. But once, okay, for example, let me assume that I open this key somewhere here that is open such that it is not working. The internal resistance will not be there. But once I close up the key for current to flow, the internal resistance will be there. And why do we have that? If there is no internal resistance, once I close this key, two things will happen. This load here, for example, let us assume is a bulb. And this is my cell. Once I close the key and there is no internal resistance to regulate the flow of current, what happens? The battery will run down immediately. The cell will run down immediately. And what happens to the bulb here? It will get sparked up. And to avoid that destruction here and the running down of cell, there exists an internal resistance whenever the source is at work. And current electricity, having run down from description down to EMF, describing to us all about EMF and everything, I think that is the conclusion and the relevant part of any examination that you need from current electricity. Thank you, and join me in the next class.